So it's, yeah, thank you.
Cool. Thanks for reminding me. All right, so let's get started right now. Let me share my screen. Can you see it normally?
Yes, that looks good.
Hey.
Okay, cool. So, hi everyone, I'm Veronica, and thanks so much for coming to my WP2 presentation. And today I'll be talking about towards faithful model explanation in NLP, a survey. And this session is an hour and a half, and I'll be talking for like a whole hour or so. So I would really appreciate it if you could only ask clarification questions in the middle and save longer discussions toward the end. All right, let's get started. So I'd like to start with an example. Imagine that it's still in the pandemic, or don't have to imagine it. And now you're asking Siri one day, hey Siri, is it safe to go to the movies without a mask now? And now suppose Siri tells you yes, no, or maybe. Well, you're probably not gonna feel super assured about this answer because you may also wonder why. In short, oftentimes, we do not only need an answer from an AI system, but also an explanation. So in this talk, I'll give you a quick tour of explainability in NLP through the lens of faithfulness. I'll first introduce the notion of explainability and faithfulness, and then I'll describe 5 categories of recent attempts at faithful explanation. And then I'll discuss their common virtues, challenges, and directions for future work, and finally, the conclusion. All right, the introduction. So everybody knows that recently end-to-end neural networks have achieved a huge success on many NLP benchmarks like GLUE and SuperGLUE, but they're still largely a black box to humans, meaning that they lack explainability. So first, what is explainability? According to the literature, explainability is the extent to which the internal mechanics of a model can be presented in understandable terms to the human. So this is kind of complicated. Let's decompose it a little bit. There are 2 parts that can be further specified. What is that internal mechanics and who is the human, right? So the answer to these 2 questions would provide a taxonomy for research in this area, actually. The first part, internal mechanics, can be either what knowledge does the model encode, or why does the model make certain predictions. And the second, a human, in other words, the target audience, can be either model developers, fellow researchers, industry practitioners, and users, and so on. In this survey, we're only going to focus on the why question. So here we're only reviewing methods that make causal claims about a model's reasoning mechanism, but not those that just make correlational ones about what the model knows. So plugging in our specifications, the working definition of this survey becomes the extent to which why a model makes certain predictions can be presented in understandable terms to some target audience. And this is going to be the scope of this survey. So now we've defined explainability, we can try to formalize some of its properties to categorize different explanations. And here I outline 6 such properties. The first is time, which is basically when the explanation happens. And this can be either post hoc, meaning that first some opaque model is given, and then an external explanation method explains it after it makes the prediction. Or it can be both in, where the explanation is produced at the same time with the prediction. The second property is called model accessibility, which is basically what parts of the model can be accessed by the explanation method. So this can be either black box access, meaning that only the model's input and output is seen, or it can be white box access, meaning that it can also see the model's internal weights. The third property is the scope of explanation, which can be either local or global. A local explanation only targets a single prediction, whereas a global explanation tries to provide insights into the model's general reasoning mechanism for the entire data distribution. And next, the fourth property is the unit of explanation, basically what it is in terms of. And this could be input features, examples, concepts, which is defined a little differently in different literature, and feature interactions, or a combination of those above. And next, we have the form of explanation, basically how it is presented to the audience. And this can be visualization, important scores, or natural language, or causal graphs, and so on. And finally, we have the target audience, as mentioned before, so I won't repeat it here. So using these properties, here is a very quick preview of the upcoming 5 categories of methods we're going to cover in this talk. And don't worry about the details right now, because we'll elaborate on each of them later. And after the properties of explanations, now we're going to look at some of its desired principles to say what is a good explanation. So we summarized 6 principles in the survey, but we're only going to focus on the first 2 here, faithfulness and plausibility. So what is faithfulness? From the literature, faithfulness means that an explanation should accurately reflect the reasoning process behind the model's prediction. In other words, it cannot lie about what's happening under the hood. And on the other hand, plausibility means that an explanation should be understandable and convincing to some target audience. What is the relationship between them? Well, there's something in common. Neither of them has an established formal definition yet, which makes it really hard to measure them quantitatively in practice. And meanwhile, there's also an intrinsic tension between them. If you think about the extreme case, the most faithful explanation could be just a copy of raw model weights, right? But this is not plausible at all, since no human could possibly understand it. And on the other extreme, the most plausible explanation could just be a copy of some human-written rationale. That would look super perfectly reasonable to the human, but has nothing to do with what the model does. So as a result, plausibility doesn't imply faithfulness and vice versa, but they're not intrinsically incompatible. So in this survey, we're gonna review existing methods from the lens of faithfulness because it is one of the most fundamental requirements of an explanation. So why is it so important? Well, first, it captures causality. Oftentimes, what is encoded in the model is not the same as what is used by the model. And in fact, people have found that models can often encode much more than they need. Some linguistic features are encoded even when they're irrelevant to the task labels. And second, an unfaithful explanation can actually be dangerous, especially if it is plausible. This is because humans are still likely to trust a model, right? Even when it doesn't work in the way we want. For example, relying on unwanted biases. And now, how do we really measure faithfulness in practice? In short, there's no established consensus yet. And however, a few different evaluation frameworks have been proposed. We can't cover all of them here. So long story short, these 4 are what we would recommend among the above, but there is a lot of caveat in using them. So please see the survey for more details. And here we're only gonna elaborate on one of them, perturbation-based evaluation. And let's think of the input to the evaluation as some feature importance ranking generated by some explanation method. So for example, a sentiment analysis model predicts positive for this sentence here, and some explanation method claims that entertaining is the most important word for the prediction, followed by funny, well, and so on. Now, perturbation-based evaluation is gonna remove a fixed proportion of features or tokens from the input based on the ranking. So if the most important features like entertaining, according to the ranking, are removed first, we should expect a large change in the model prediction. By contrast, if the least important ones are first removed, like the dash, the change should be small, right? And if its random features are removed first, the change should be expected to be somewhere in the middle. So we can compare the actual resulting changes using the ranking provided by different explanation methods. And those that align with all these expectations above are considered more faithful. So that is the perturbation evaluation for faithfulness.
Could you clarify what you mean by remove?
Oh, yes.
You're going to
So
delete the word.
removing can
If you
be
delete the word entertaining, it's not grammatical anymore. So I don't quite know what you mean by remove.
right. So one way of removing it is to replace it by the mask token, the special token in some language models, right? But
Got it.
that for sure would result in the ungrammatical problem, as you said, and we're gonna talk about that later. So let's go to, oh yeah, so that was the introduction, and now let's move on to section 2, prior attempts at faithful explanation. So I would categorize recent advances in this field into 5 categories: similarity methods, analysis of model internal structures, backpropagation-based methods, counterfactual intervention, and self-explanatory models. Because of time, we're only gonna elaborate on a few representative works in each of the category, but feel free to see the survey for a total of 90 plus if you have the patience. All right, so throughout the section, we'll use this run example to give you an intuition of how the simplest version of these methods work. So suppose we have this sentiment classification model, and given the sentence, "the movie is great, I love it," it predicts positive. Now, our goal is to answer this question: what features or tokens are the most important for the model's prediction? So let's look at similarity methods first. Similarity methods are post hoc and typically provide example-based explanations. So given a test example, it's going to find its most similar training examples in the model's learned representation space to justify the current prediction. Note that this is the learned space, not the input space. And this is akin to how we humans would justify our actions by analogy, right? Like doctors making diagnoses based on past cases. And on the run example, given this input sentence, it's going to retrieve its most similar training examples in the learned space. For example, this movie is awesome, I love it. This movie is awesome, I like it, and so on. And these examples are going to constitute the explanation or justification of the current prediction. And this is what we call example-based explanations. There is not a lot of existing work in this category. Karana et al. First theoretically formalized this method in 1999, which is exactly what we've just seen on the run example. And several follow-up studies explore different extensions to it. We'll point you to the relevant section in the survey for more details. In summary, the advantages of similarity methods include: first, they're intuitive to understand. Second, they're easy to implement as no retraining or data manipulation is needed. The similarity scores are just available by simply passing the examples through the trained model. And third, they're also highly model agnostic, since all kinds of neural networks would have some representation space, and any similarity metric like cosine can be applied. But they also have some disadvantages. First, they only provide the outcome of the model's reasoning process, which is which examples are considered similar in the learned space. But this does not shed light on how the model reasons, which is how the space is learned, right? And second, existing studies are mostly evaluated with plausibility only, but rarely on faithfulness. So it is really questionable whether similarity methods can truly establish causality between the model prediction and the explanation, since there's no guarantee the model really reasons in a similar fashion for similar examples. And that was the first method. Next up is the analysis of model internal structures. So this is also a post hoc method, and white box method, which can be either local or global. And there are two things in the name analysis of model internal structures. The first is what are the structures, right? So this can be neurons, layers, or specific mechanism like convolution or attention. And second, how do we analyze those structures? This could be visualization, clustering, or correlation and analysis, and so on. On our running example, here is a visualization of the weights of the so-called attention layer, which is a specific mechanism in the model. So the initial CLS token is a special token used for classification in the end. So it's considered the intermediate output. I could see that CLS attends most to grade, love, and the SEP token, which is another special token. So the attention-based explanation is going to claim that these three are the most important tokens for the prediction. And past work in this category can be classified into the pre-attention era and post-attention era, since attention has so greatly reshaped this area of research. And pre-attention era includes the analysis of neurons with specific purposes, like neurons that only turn on inside quotes, or the analysis of inputs with specific activation patterns. For example, phrases like not plus an adjective will cluster together in the representation space, and so do phrases like adverb plus adjective. In the post-attention era, a lot of efforts have been devoted into analyzing attention, since it's the core of transformers. And transformers is arguably the most widely adopted architecture in NLP nowadays. And that's probably why a lot of work has been devoted into analyzing attention. So we'll give a brief refresher on attention here. Simply put, attention is a sequence-to-sequence function, which takes in as input a sequence of vectors x, y through xn, where each vector is just a word representation. And the output is another sequence of vectors of the same length, y1 through yn. And each yj vector is a weighted sum of all the xi vectors. And the weights, aij here, is called attention weights. So you can think of the attention weights, aij, as the amount of attention in human terms the output is paying to the feature xi. So this is often intuitively understood as representing feature importance for the model prediction, as what we said in the run example. But is it really so? There has been really a long debate on this. A famous paper called Attention is Not Explanation says that we can actually construct adversarial attention distributions, which are maximally different from the model's original attention distribution, but minimally influence the prediction. So for example, on this movie review here, which is predicted negative, the model initially has the highest attention weights on the word waste and asking, which seems intuitive to humans, right? But when the authors try to manually change these weights, they realize that it's possible to actually make the model to pay attention to uninformative words like myself and was instead, without much influence on the prediction. So by this and a few other reasons, the authors argue that attention should not be viewed as explanation. However, not everyone is convinced. Another paper called Attention is Not Explanation then came out, and one of their core arguments is adversarial distributions are not adversarial weights. That means even though it's possible to manipulate the weights to make the model attend to uninformative words, the model itself is not likely to converge to those weights naturally through training. So we should not worry too much, since such adversarial weights would not naturally exist. And there are many follow-ups along this line, including direct counter-arguments to this and explorations into how we can remedy attention toward a more faithful explanation. And we encourage you to read more in this section later. So in summary, there are a few advantages of the analysis of model internal structures. First, they are intuitive to understand, especially for end users, since the form is often visualization. Second, model weights are easily accessible and computationally efficient. Third, there are many interactive tools which can help the user form the hypotheses about their data and models and dynamically adjust them through testing. Finally, attention can capture the interaction between features, whereas many other methods, as we will cover later, only capture the flat importance score of individual features. And the disadvantages include, first, the faithfulness is questionable. Attention may not necessarily represent causal contribution, as we just mentioned in the debate. Second, we often interpret attention weights as on the hidden states as the importance of input tokens, right? However, a hidden state may not really represent its corresponding input token because of contextual information mingled in from other tokens. And third, attention weights reflect what happens at a single.
זה הוא אמר לי את זה.
Sorry, I hear some noise here. All right, so let's continue. Wait, I'm gonna, let's see.
I think Rotom is unmuted, so you could just mute her.
Oh, let me see, how do I do that?
זהו, זה הקטע שכאילו
If you
בתכנון
click on
המקורי אין
the
מיוט.
participants list, then there'll be a little button next to her name where you
Got
can
it.
choose to
I'll
mute.
mute all, including Chris, since I didn't find the mute. Right. Cool. Wait. Okay, cool. Let's continue. The third disadvantage of analysis of model internal structures is that attention weights can only reflect what happens at a single time step only, right? But not take the whole computation path into account. And that was the second category. The third one is called backpropagation-based methods. This is still a post hoc, white box, local method, and it includes two subcategories, gradient methods and propagation methods. What is in common between them is that they both identify the contribution of input features via a backward path through the model, therefore propagating the importance or relevance from the output to the input layer. And what's different is that the former gradient methods follow standard backpropagation rules, but propagation methods would define custom rules for each different layer type. And we'll only focus on gradient methods here, but you're certainly welcome to read more in the survey. So going back to our run example, here we have the input tokens x1 through xn and the output label y. And now backpropagation methods are going to compute the gradients or some variant of it of the output y with respect to each feature xi as the importance or relevance of that feature. So say in our case, the word great and love has the largest gradient, so they are going to be considered the most relevant for the prediction. And intuitively, this would make sense, right? Because gradient just means how much difference a tiny change in the input would make to the output. So in this sense, it does capture the importance of the feature. And most ideas in this category stem from computer vision. To formalize different methods, we're going to define a couple of notations. And I know it's hard, but please try to keep those in mind since we're going to use them heavily afterwards. So X is the input example with features Xi, and M is the model, Y equals MX is the model's prediction. And the most important thing, Ri of X is the relevance of each feature, Xi to Y. And finally, one optional baseline, X bar, is some baseline input to compare against the input X, which could be an all black image or an all zero sentence. And with these notations, we're now ready to formalize different methods. Gradient methods follow standard backpropagation rules, as we just said, and they treat the gradient or some variant of that output with respect to each input feature as the relevance. And specific gradient methods only differ in how they define that Ri of X, the relevance of each feature. And the most straightforward method is called simple gradients. It simply computes the gradient itself or some magnitude of it as the relevance, which is what we just illustrated in the run example. And here in this toy two-dimensional space, we're trying to classify a point into red or blue. So if we take the gradient of the dot over here, it's going to be nearly 0 along the x2 direction, right? Which tells us that in this locality of the dot, it is the feature x1 that makes the difference. And there are also obvious problems with simple gradients. First, it only measures the sensitivity of the output with respect to changes in the feature, but actually not the contribution of the feature to the output. What do I mean by this? For example, if you think of a saturated function like sigmoid over here. So if x is large, its gradient is going to be very small, but the function value is large. So this means that the feature itself could constitute a large proportion in the output, but gradient simply cannot capture this. And second, simple gradients are very local because they can change drastically with subtle changes in the input. In this example, if we just move this dot a little bit around this neighborhood, then the gradient is going to be very unstable. So this could result in empirically noisy explanations. To address that issue, to address the first issue, the sensitivity issue, people then say, okay, why don't we take the input itself into account? So they propose this gradient times input method, which computes the relevance as the inner product of the gradient and the input. So then this can intuitively measure the contribution of that feature instead of just the sensitivity of the output. But there's another problem. There's a sanity check called input sensitivity test, which says that if two inputs only differ at one feature and lead to different model predictions, then the explanation should assign no importance to the feature. That intuitively makes sense, right? Because only the sole difference in that one feature result in different predictions. So that feature must have been informative to the model. But gradient times input fails this test. For example, suppose we have this simple model, mx is 1 minus max of 0 and 1 minus x, then it's gonna have different outputs on 0 and 2. But gradient times input would have the same explanation for them. So to solve that issue, another method called integrated gradients was proposed. It makes use of the baseline input, as we just said, the x bar, which is typically an all 0 input. And then it would average gradients along the path from the baseline to the input as the relevance. So formally, we would first interpolate points along the path between the baseline and the input, as shown on the figure, and then we'll compute the gradient for each interpolated point along this path. Next, we compute an approximated integral of those gradients. Finally, we will rescale the results for it to remain in the original space, and this is the relevance. So this method is shown to satisfy the input sensitivity test we said just now, but it's not perfect either. Empirically, it is found to be still visually noisy in CV. For instance, on these image classification examples, integrated gradients provide a vague outline of the object, but it's not super clear, right? So some researchers hypothesize that this is still due to that the simple gradients are too local, as we just said. Thus, they propose a new method to solve the noisy problem. You can see that here it does result in cleaner visualizations. And how exactly did they do that? The method is so-called removing noise by adding noise. They create several local copies of the input by adding Gaussian noise to it, as shown on the figure, and then they compute the gradient for each copy and average them as the relevance. So that is the smooth grad method. In summary, here's how each gradient method computes the relevance. And don't worry if you already forget this formula, because let's now look at how they work on a concrete example in language. So still the sentiment classification task. Given the sentence, this is said to be the best movie of the year, but I was almost asleep. Our model says it's positive, which is wrong, right? But the model is not super sure. Now let's see what different gradient methods say about this. So here we show the 3 most important words claimed by the explanation for the model prediction. And the darkest is the most important. So simple gradients don't seem to tell us anything really informative in particular. And integrated gradients claim that the model thinks best, asleep, and sad are the most important words, but best outweighs the other 2. So this seems to intuitively align with the model's positive prediction, right? And smoothgrad shows that this shows the same 3 words, but here asleep and sad are more important, which seems to be inconsistent with the prediction. And note that here we are only judging if a prediction makes sense to us only with plausibility, but not necessarily with faithfulness. So that was all I want to say about gradient methods. If you're also interested in the propagation-based ones, please do check out the survey. All right, in summary, the advantages of backpropagation methods are, first, they are relatively easy to compute, requiring only a few calls to the model's backward function. And in terms of faithfulness, gradients are intrinsically tied to the influence of the input features on the prediction. And empirically, a few recent methods do report faithfulness evaluation results based on perturbation-based evaluation. And they're shown to be more faithful than previous baselines. Finally, unlike the analysis of model internal structures, backpropagation-based methods do take the entire computation path into account. But there are also disadvantages. First, most existing work only target low-level features like pixels or input tokens. So it is really not intuitive how to compute any sort of gradient with respect to higher level features like, say, part of speech or syntax. Second, it is not obvious at all how these methods can be applied to non-classification tasks, especially those with multiple outputs like language generation, right? And then the explanation can be unstable, which is minimally different inputs can lead to drastically different relevance maps. Finally, in terms of faithfulness, still a lot of methods do not report evaluation results at all. And also there is actually negative evidence. Certain methods are only doing input recovery, which is totally irrelevant to what the model is doing. All right, so that was the 3rd method and 2 to go. And here comes counterfactual intervention. This is still a post-hoc method. At first, we're gonna understand what does it mean by counterfactual. So this concept originates from social science, where counterfactual reasoning means given 2 co-occurring events, A and B, A is said to cause B if under some hypothetical counterfactual case that A did not occur, B would also have not occurred. And in machine learning, we can think of A as the unit of explanation. For example, the example, feature, or neuron, and B as the model output. And now we need to control. So in the process, we need to control for all events other than A in this process, or otherwise we cannot isolate the change in B solely to A, right? So on our run example, say our goal is to know how important the word great is. Now we're going to answer this question by changing this token in the input. For example, by masking it out or replacing it with other tokens like okay or bad, and observe the resulting change in the prediction. The larger the change, the more important the token is claimed by this counterfactual intervention method. And in the literature, the masking method is called leave one out. The replacing method is called counterfactual examples or contrast sets. Existing work in this category can be classified based on 3 questions. First, what is being intervened in? This can be the input or the model representation. Second, what is the specific target of the intervention? Under input, this can be either the input feature or the entire input example. Under model representation, this can be either individual neurons or higher level feature representations. Finally, what is the intervention operation? So this can be either erasure, which is simply deleting the target, or perturbation, which is to change the value of the target. And this is the case for both input and model representation. So each of the paths above is a different type of counterfactual intervention. And we'll only elaborate on one of them here, which is the red path, feature representation-based erasure. Please read more in the survey if you're interested. To illustrate this method using one concrete scenario, suppose our goal is to answer is some feature used by the model in some task. So for instance, the feature can be part of speech and the task can be word prediction. Say in predicting this mask token in the sentence, the dog mask, does the model use the fact that mask should be a verb? How do we answer this question? So intuitively, if we follow the idea of counterfactual reasoning, we could erase the part of speech feature from the model representation and observe the change in the word prediction performance. One method of this type is called amnesic probing. Given a word prediction model like birds and the input sentence, the dog ran, it would feed the input sentence into birds and obtain token representations. And then using the vector for ran called hran, we're going to first check if the model actually knows part of speech. And the technique is called standard probing on the left-hand side. This means we would freeze hran and train a simple classifier on top to predict its part of speech. So here we see that it really has good accuracy because it predicts verb as the most likely part of speech. So if the linear classifier performs well like this, we're going to proceed. Otherwise, we just abort since the model itself doesn't even know part of speech. So let alone use it in the end task, right? And in parallel, we're going to use the same hran to do the word prediction task as usual on the right-hand side. Next up is the amnesic operation, which essentially removes part of speech from hran. And don't worry about how it actually works right now. Just assume that it works and we have removed it. Now we have a new hran without part of speech info. So with this, we're going to do another round of standard probing for part of speech just to check that it really does not encode that feature anymore. So here we see that it has equal probabilities for all different part of speech labels. And finally, we'll use the new hran to do word prediction task again. If the prediction changes a lot, then we would conclude part of speech was indeed used by the model. Otherwise, it's probably not very relevant for the task. So this is the high-level overview of amnesic probing. Now we still have one question left, which is, what is that amnesic operation? In that paper, the authors use a method called iterative null space projection as the amnesic operation. Say we have this toy scenario where part of speech is represented by triangle versus circles here. And for example, the triangles can be thought of as verbs and circles nouns. And X is an input representation like the hran we just saw. And now our goal is to remove the part of speech feature from the model representation space. So the INLP method works as follows. We first would train a linear classifier W in the original space of X to predict the target feature, triangle versus circle. And then we'll project the representation X onto V, the null space of W. So note that after this, we've effectively nullified W since W times any X in its input space are gonna be 0, right? So W cannot predict that feature anymore. In other words, we've removed the target feature linearly encoded by W. And finally, we're going to repeat 1 and 2 until there is no such W with above random performance. After all this, we've removed the target feature altogether linearly. So using INLP, the amnesic probing paper finds some interesting observations. So some linguistic features like part of speech, dependence, and tree named entity are indeed used in word prediction. But some others like constituency boundary, which is the start and end of phrases, seem not used. And coming back to faithfulness, is the method really faithful by construction? Well, there's still one possible pitfall. When removing part of speech, we might have incidentally touched on other correlating features like syntax, for example. How do we know that we only removed what we want? The authors did a sanity check on this. After the removal, they would explicitly append the removed feature back onto the representation and redo the word prediction task. If the performance can be restored, then we haven't removed too much, right? Empirically, this is found to be the case for most of the features, so we're good. All right, so several advantages of counterfactual intervention. First, they are rooted in causality literature, and it's designed to capture causal instead of mere correlation effects between inputs and outputs. Second, compared to other methods, they are often explicitly evaluated in terms of faithfulness. Finally, several methods like amnesic probing we just talked about really capture the contribution of higher level features instead of just input tokens. But they also have some disadvantages. First, as Lyle pointed out, erasure-based intervention can result in nonsensical inputs. For example, just drop in a token in a sentence would make it ungrammatical. And second, intervening in a single feature relies on the assumption that features are independent, right? And only then we can isolate the influence of a single feature. For example, in this sentence, a negative movie review called the movie is mediocre or maybe even bad. If we individually delete the token mediocre or bad, the sentence is still going to be negative, right? Does that mean neither of the tokens are important? No, this is because only the counterfactual intervention, which deletes one feature at a time, cannot capture this or relation between the tokens. Also, there are two other more complicated disadvantages that we cannot explain here, but you're welcome to read more in the paper, in the survey. All right, that was the fourth one. We have one left, self-explanatory models. Self-explanatory models provide built-in explanations in various forms. And all of the above post hoc methods that we just talked about can be unfaithful. So people thought, what if we just let the model explain itself? Self-explanatory models would provide both the task prediction and the explanation at the same time, and both components can be supervised. On our running example, the model takes in the sentence, outputs a label, as well as an explanation like the words great and love indicate that the person feels positive about the movie, and both components are trainable. So past work in this family can be classified into two types broadly. The first is called explainable architecture, and this means that the model architecture itself is transparent such that no extra explanation is necessary. This includes neural module networks, neural symbolic models, and models with constraints. And the second type is generating explanations. This means that the model may still have a non-transparent structure, but it generates an explicit explanation as a byproduct of the inference process. This would include predict, then explain, explain, then predict, and jointly predict and explain. So we are going to talk about only two subcategories here, but feel free to read more in the survey. So let's look at these two in comparison. Predict, then explain has a predictor, that directly operates on the input, and then an explainer that takes in the prediction along with the input to generate an explanation. By contrast, explain then predict first generates the explanation. Then the predictor needs to make the prediction only based on that explanation, but not the input. One example of the first type is Camberley et al.'s work. They designed a self-explanatory model for natural language inference, which is the task to determine if a premise entails a hypothesis. They collected a data set called ESNI, which is an extension of SNI, the Stanford Natural Language Inference dataset, by adding human-provided explanations. For example, given this premise, a man in an orange vest leans on a pickup truck, and the hypothesis, a man is stuck in a truck, the label should be entailment. And they extend this dataset by adding this human-written explanation. Man leans on a pickup truck implies that he's touching it. They train a model like this on this dataset, supervising both the explainer and the predictor. So the explainer on the left-hand side takes in the premise and the hypothesis, predicts a label, which is then fed into the explainer along with the premise and hypothesis to generate an explanation. One obvious problem about this predict and explain framework is still faithfulness. Since the predictor doesn't have to depend on the explainer, the model is just like any other previous post hoc methods, right? The predictor could make the prediction in whatever reasoning mechanism it likes, and then the explainer could generate a totally different explanation. So naturally, people turn to another framework called explain then predict. Here, the predictor can only access the explanation but not the input. Why? Well, if it can access the input, then it can still make the prediction in whatever fashion it likes, which brings us back to the same pitfall. So the example is still from Camberley et al.'s work. They designed this other model to compare with the previous one. Here, the explainer takes both the premise and the hypothesis to generate an explanation first, which is then given to the predictor to output a label. In comparison to the previous predict then explain, this model here has slightly worse label accuracy on NLI, but better explanation plausibility. Explain then predict seems faithful by construction, right? But is it really so? We've ignored just one more pitfall. The explanation here may contain spurious cues to the label. For example, if we see an explanation in the form of like X is a type of Y, X implies Y, or X is the same as Y, it is almost always associated with entailment. And similar templates exist for other labels. So the predictor can trivially make a prediction by just looking at what the form of the explanation is. To address this issue, people thought of a fix. What if we don't just generate one explanation, but an explanation for every candidate label? Kumar and Talukdar tried this idea on still NLI, proposing this Nile model. It would take in the premise and the hypothesis, generate a candidate explanation for each possible label. And then all of these are fed to the predictor, which then makes a decision. So this would solve the problem of spurious cues, since the predictor now sees all three. In summary, the advantages of self-explanatory models are, first, there is no need for any post hoc explanations. And second, the form is flexible, right? It could be model architecture, input features, natural language, or causal graphs. And then we can supervise the explainer with human-provided explanations, and therefore we encourage the model to rely on desired human-like reasoning mechanisms instead of just spurious cues. Fourth, we see that certain self-explanatory models are really faithful by construction. Although we have to be super extra cautious about this claim, since some of the seemingly faithful by construction methods, like the explain then predict framework we just talked about, are actually not faithful. There are disadvantages First, still many self-explanatory models cannot guarantee faithfulness. Second, there's often an observed trade-off between performance and interpretability in self-explanatory models. Third, large-scale human supervision on explanations can be costly and noisy. And finally, although even if we have good quality human supervision, it is really hard to automatically evaluate the quality of model-generated ones, given the reference, since there can be multiple ways to explain a prediction. All right, now we've finished all 5 methods, and congratulations on bearing with me until here. Let's now move on to a very quick discussion of the common virtues and limitations of these methods. So virtues, all the above research, first, is conducive to bridging the gap between competence and performance in language models. So these 2 terms originate from linguistics. Competence describes our unconscious knowledge of a language, whereas performance refers to our actual use of the knowledge. For humans, there's often a gap between these 2. For example, we can theoretically say a sentence with infinitely many embedded clauses, but in practice will never do so. And similarly for language models, what they know can be different from what they use, right? Previous work on interpretability predominantly focuses on only competence, but more recent studies, like all 5 methods we've just discussed, aim at answering the performance question. And this would allow us to better understand whether the same gap exists for language models as they do for humans. Second, there has been increasing awareness of faithfulness and other principles of explanation methods. And a number of different evaluation methods have been proposed, though each evaluation framework has specific assumptions and application scenarios. This is at least a good starting point for quantitatively assessing the quality of explanations. Third, usually explanations produced by most of the above methods are intuitive to understand, even for lay people, since the form of them are simple. And next, there are a plethora of explanation methods that are model agnostic, especially for classification tasks, like the backpropagation methods we just said. Then, many studies draw insights from work in computer vision and develop adaptable methods in language. Also, for example, the backpropagation methods we just said. Finally, there are a lot of toolkits developed to help users apply these explanation methods to their own models. And please see the survey if you want a list. And despite all of these advances, the area still faces several major challenges, which also provide exciting future work opportunities. First, a large number of explanation methods still lack objective quality evaluations, especially in terms of faithfulness. And there has not been any established standard on how to measure faithfulness. So we need a universal framework, which is fundamental to measuring any progress in this research area. And most existing methods provide explanations in terms of surface level features only. For example, pixels and vision and tokens in language. The future work should explore how to capture the contribution of higher level features in a task, including linguistic and extra-linguistic ones. Next, most existing methods capture the contribution of individual features only, but not their higher order interactions, like we just said for the counterfactual intervention case. So future work could develop more flexible forms of explanation instead of just the importance scores, like feature subsets or causal graphs. Next, existing work mostly focuses on limited task formats like classification and span identification like QA. This limits their downstream applicability to real-world scenarios. So future work could study alternative task formats such as language generation, and structured prediction, or even better, develop some generalizable methods across tasks. Next, it is not always obvious whether these insights from model explanations are actionable, right? For example, suppose some local explanation method tells you that the model is not using the desired features on the test example. How would you go about fixing it? How would you communicate with the model? To this end, interactive explanations will be a fruitful area for future study. And several recent studies on knowledge editing have shown the plausibility of this idea. Finally, there has been a tension between model performance and interpretability, especially evident in the self-explanatory models. So it would be really helpful if we could have a theoretical understanding of whether that tension is intrinsic or avoidable. And in the meantime, we need to be extra cautious to balance between performance and interpretability, depending on our specific application scenario. All right, that was everything. And now let's go to the conclusion. So this survey provides an extensive tour of recent advances in NLP explainability through the lens of faithfulness. We discuss the notion of faithfulness and present a critical review of 5 categories of existing model explanation methods. Now we summarize all of the above methods by discussing the common virtues, challenges, as well as future research directions. Finally, we hope the survey could provide an overview of the area for researchers interested in interpretability, as well as developers aiming at better understanding their own models. That was everything about the presentation. Thanks for listening. And now I'm happy to take questions.
Very nice work. So Charles, as the chair, you can pick the order of the question answers. Typically, we start with the committee. We often will go inside out from the most distantly related to the most closely related to the student, but the order's up to you. So the committee is you and Lyle and me and Mariana. And
No, I'm
Mariana
not
and
on
I
the
are super-
committee. I'm
Oh, okay.
You're welcome to ask questions.
I'm happy to heckle and have lots of questions. I have no
Sorry,
official role.
apologies. Okay, so
I think Mariana should ask the first question, maybe followed by Chris. And I'm actually the most distantly related, and so my comments would be of probably a slightly different nature. So.
Okay, great. So I'll start. I find the synthesis that you made, Veronica, really amazing. Like of such a large number of methods, and it's really like, even when I read the manuscript, I felt like I was learning a lot of things, and yeah, it's really amazing how you managed to synthesize all this information in such a comprehensive and very clear way. So yes, one question that I have is that I found very interesting, this parallelism that you make between human performance and competence and performance, and what happens in the models. So you said that previous probing interpretability studies, they tried to explore the competence of the model, so what knowledge they have about the language, and that these methods which are more aimed towards explainability and faithfulness would focus more on the performance, so what knowledge the models actually use to perform the tasks that they are used to, right? So I wonder, what's your opinion about this? Like, do you think that we should focus on performance and just abandon competence? Like, do we still need to care about what the model knows, what it has learned about language, if it's not using this knowledge in downstream tasks? Why, and if it's interesting, why would this be interesting? And if it's not interesting, how you would suggest to proceed? Just like look at different tasks and how the models use the knowledge in these tasks, like in each separate task. Yeah,
that's a great question. That's a really great question. So what I think is the most interesting is to first understand what the competence and performance for models are, and then to find if there is any gap between them, right? So one example is from L.E. Pavlik's research, which tries to measure like what information the model encodes beforehand, and then measure the extractability or accessibility of them in downstream tasks. So they do find different kinds of knowledge and different kinds of tasks would result in a different kind of gap. So that really reinforces that there is really a gap for models as well, just like for humans. So I think that is really an interesting area of research.
Okay, so you think that we should continue doing both and try to identify whether there is a gap in specific tasks, or just abandon competence and look at what information the models actually use?
No, I think the prerequisite to understanding the gap is to first understanding both of them individually, right? So if we do not know what the competence is, how should we know what the gap is, right?
So it is important to know the gap. It is not only important to know what knowledge is actually used by the models. We need to know about this gap.
Yeah, I think that's at least interesting scientifically. Not sure if it's practically interesting.
I mean, from a linguistics point of view, it's definitely super interesting. Like, I wonder, like, in this interpretability and explainability vague of research, whether it would still be super relevant as it is in the linguistics literature. That's why
I think so.
I asked this question. Okay, great. I think so too. I agree. Okay, and I have another question as well. So you said that when you do the in methods which do this counterfactual intervention, we can delete, we can erase features, or we can remove higher level, features which fall in groups describing higher level features. Like, we can remove all information about syntax, for example, or about part of speech, right? So yeah, well, if we erase words, Laia asked a clarification question during your talk, or like it was more like a comment saying that if you erase words, then you get ungrammatical sentences, right? So that's one thing. And the other question that you ask in your manuscript, but there's no answer, and this is why I'm asking you this question right now, is, do you think that they, like if you remove syntax, do you, sorry, yeah, I tried to find how you had written it in the manuscript itself. Yeah, you said, since syntax is such a fundamental component of language, what does it mean if a language model is entirely ignorant of syntax?
Right.
Is it still a language model at all?
Yes, that is a great question. Yeah, so that's a great question, and that's why I think it is one of the limitations of the counterfactual reasoning framework. So in my categorization framework, I said that all of these are different paths, right? So counterfactual reasoning was a feature representation targeted erasure, but another path, which is feature representation targeted perturbation, would address that problem you said. So instead of just deleting a single feature like part of speech or syntax, they would try to perturb or change the value of that feature. So one example is another method that I covered in the survey but did not have the chance to cover in the talk, and that is called alter rep, which instead of just removing syntax tree, they would try to manually, not manually, but manipulate the syntax tree into another syntax tree. So let the model think that there is an alternative syntax tree to the current sentence. So in that sense, it will result in less of the nonsensical input problem, since the language model is still a language model, right? It's still no syntax. It's just that it has a different interpretation of the current sentence. I think that's an interesting area of research.
Mm-hmm. Okay, so it's more of a transformation than completely erasing or removing a specific type of information.
Right.
Okay, great. Thank you, Veronica. These were my two questions.
Thanks, Veronica. This is a very impressive piece of scholarship. I agree absolutely with Mariana that this is a really amazing synthesis, and I feel like I learned a tremendous amount. So thank you so much for that. So that being said, I'm going to ask questions that are now unfair because they go beyond the scope of what you did.
Okay,
But
sure.
so I guess I want to take like a step back and look at this from the higher level. And then I wonder if you could possibly make design recommendations for models that we want to be explainable. I guess like first, I'm interested in why are explainable models important? And then if we're, rather than saying, how do we evaluate the explainability of current models, like what should be our guiding light when we're designing models in the future in order to make them explainable, and why is that important?
Right. So are you asking in the sense of self-explanatory models?
I think I'm asking you to take a stand. So I want you to make an argument for why it's important to have models that are explainable from whatever reason you want. I think it can go beyond just the scientific point of view to the usage point of view. And then if like once you've convinced us that they are important, then if you were giving guidance to people who are designing future models, what would be your guidance on properties that they should include in their models to make them better and more explainable?
Yes. So luckily, I have a backup slide for this. Can you still see it? So
Yeah,
as I
perfect.
understand, the first piece of the question is, why is it important to have explanatory models that are explainable? So obviously, explainability would allow us to do a couple of different things. For example, it allows us to discover dataset artifacts, say like the famous hypothesis only Q in some famous NLI-based datasets. If we could have explainable models.
Yeah, maybe
Oh,
I
sorry.
think for other, I know what you're talking about, but maybe you could unpack that for other people just to
Okay. Oh,
explain
sorry.
what.
So NLI is a task where you need to judge if a premise entails a hypothesis, right? So essentially, theoretically, you need both of the inputs to make a decision. But surprisingly, some people found that only using the hypothesis itself, you could still reach above chance accuracy. So that means there are cues in the hypotheses that would correlate accidentally with the label that allows you to make a trivial prediction. So that's like one kind of dataset artifact. So explainability would allow us to discover such dataset artifacts. And the second thing is that explainable models would allow us to diagnose what its strengths and weaknesses are. And we could debug it. For example, if we notice that a model is relying on like gender biases, we could try to eliminate that bias by recasting the model or manipulating its representation or whatever to try to make it more to behave in a more desired way, right? And finally, it could enhance user trust in some high-stake applications, like whether you would like hiring decisions or health or law or finance. So in those cases, an answer is not just enough, right? You need an explanation to be convinced. So these are reasons that why I think explainable models would be important. And the second piece of the question is design guidelines.
So sorry, before we hop onto the design guidelines. So I think these are all great reasons. I actually order them in the reverse order, right? Number one, most important is your third bullet point there, like user trust in the model. I think that's like, I feel like that's a guiding light that you should, if you go forward with this as your main topic for your thesis, like that is a super important aspect that I think we're all going to face in the future of artificial intelligence. And then the other two I sort of feel like are secondary to that. So diagnosing the model strength and weakness, great, after you've established trust, and then data set artifacts are kind of a debugging element. So yeah, so excellent picks. I just want to prioritize them differently.
Yeah, I should have said that these three are not ordered in any particular order. Maybe from the more low level to a more high level order. But I agree with you that user trust is actually very fundamental. So the second piece of the question, as I understand, are you asking about design principles of self-explanatory models or explanation methods?
Of explanatory models that can be explained, self-explanatory models.
So If I can go back to the several categories of self-explanatory models. So if you remember, all right, so if you remember here, I had this framework of current methods. So I have actually very specific low-level suggestions on each of those types, but I can give an example of say probably the first the first type, the neural module networks, right? All right. So this is a kind of model that would decompose a question or an input into different modules. Like here, you decompose the question into different like symbolic operations that you would perform on some input, right? So this is an example from Nitish's thesis, who just graduated. But anyway, so for this kind of network, it seems that it's faithful by construction, right? Because by only looking at the architecture of the model, you're gonna be able to interpret how it makes the decision, right? But one design principle that I would suggest for this specific type of models is that you need to ensure that each of these modules are actually faithful. What does that mean? So some people would try to train these kind of neural module networks end to end. So they will only give it the input and the answer and expect the internal modules to perform the actions that they are intended to perform. But people actually found that it's possible for some of the modules to actually deviate from their names. Say the relocate function here can actually do not do relocate, but instead just answer the question end to end, and the internal and the other modules just do nothing, right? So that's a possible learning path. So one suggestion I would have for this type of models is that you need to have some kind of internal supervision for each specific modules for them to be faithful. And that's just one very low level design principle, but there are others, but I would say the suggestions for each of them are going to be very different depending on specific type and task. But I guess a higher level suggestion would just be try to stick to the principles that we outlined before, the 6, like including faithfulness, possibility, input sensitivity, and so on. Yeah, that was my answer.
Great. And do you feel like any particular set of the models that you've examined in your literature survey are more promising than
Yes.
others?
Yes. So very personally, I think neural module networks, neurosymbolic models with constraints, as well as explain then predict, are promising, but the other two, I guess, are less promising because most of the existing work I've seen or I've covered in my survey have more of a faithfulness problem.
Great, thanks. I'll hand
Thank you.
over to you, Charles.
Thanks. Yeah, this is really a great presentation. I was really amazed by how much you were able to, pack everything, so many papers in one document, but methodically with a clear vision of where you're going. I really learned a tremendous amount from this. So thank you for that. It's also good to see some of the work that's no longer familiar to me. So I guess my question actually has a little bit to do with both Mariana's and also Chris's. I think, and relates back to one of the last points you made when you talked about, I think, the limited task format. Right. So a lot of cases we're looking at here is a prediction task or classification task. That's a fairly inadequate characterization of language. I'm just going to give you one example, right? So say, for instance, subject-verb agreement has been done to death. But so we can have a sentence like, say, the student and the committee members are nice. Okay, fine. Or the committee members and a student are nice. But what if you do things like the committee members or the student nice? Do you say are or is?
I actually don't know.
No, yeah, right, exactly right. So there, there are lots of cases, like this where I mean, this is the most basic thing, right? I mean, you can talk about things in morphology, in phonology, in syntax, and semantics. There are a lot of the things that really shows that language isn't a total function, if you will. So the thought is totally clear, but there's no linguistic form responsible for it. So now you can shoehorn people into a classification task or decision task and do it. If you give people, you put people in front of a computer and say choose one of two options, you may get some sort of distribution, but it's by no means a genuine reflection of what people know about the grammar of English. So this goes back to the competence and performance problem. That is that the competence, so the absence of an answer does have in a performance task, namely are or is, does have a competence answer. For example, there are, we don't need to go into the theories of how the things work, but I think what we're seeing here is really possibly a disconnect between the theories of language. I mean, explanatory theories of language, the things that are understandable on the one hand, and the kind of tasks or the tools we'll be used to in probing the nature of these NLP systems. So I think you really hit a nail on the head that we really need a more expansive list of suite of tests for us to really get to the problem of what's really going on and how to explain the performance of the systems. So I would like to hear you maybe expanding a little bit on that to address these problems.
Yeah, that is a really interesting question. So if I understand correctly, at least one of the examples you suggested is the lack of answer problem, right? So I think the first step in proposing a resolution to that issue is that we probably need to find a good representation for this lack of answer in language models, right? So as you said, we could probably represent it as a distribution, but maybe that's not a faithful enough representation of what human knows, right? So I'm actually interested to know like how people or how the linguistics community would represent this like undecided nature of the answer. This is really I really don't know like what is a good way to do it.
Right. I mean, we can go into that, but a distribution wouldn't do it. So for instance, there are many ways of saying the same thing, both are fine, and all of them are fine. There may be a statistical distribution over the percentage of time people say it or how many people say. You can say, I gave John a book, or you can also say I give a book to John. I mean, those two answers are interchangeable. There's going to be a probabilistic distribution out there that we can fit and measure. But this is different. I mean, so this is I think it's really a fact of, in this case, I mean, it's really it's just not a total function. It's not defined for some input attributes. And so, I think my view is that there may, so there should be category of output that cause, I don't know, right? So I'm wondering whether maybe this something like that could be included in the suggestions going forward, and if so, how does one approach that?
Yeah, I think so maybe this is a little bit of a detour, but the suggestion of including the I don't know option has been actually done, at least for some tasks like question answering. So one of our previous papers on like question answering and event extraction would explicitly include the label I don't know as one of the choices. So that is not a perfect solution, of course, but at least the model has the option to like explicitly say I don't know. But so that is one possible thing that we could do. And I would imagine if you could formalize I don't know, like an explicit label, then you you could actually apply existing explanation methods to that, right? Since it's still a label in the classification task. So you could like, visualize the gradients or some variance of the I don't know label with respect to different features. So that is a naive solution, but I'm sure there's maybe a more mature representation other than just I don't know.
So is Lyle still here? Or I guess we can open up the floor to everybody for questions, right? That's a better procedure.
Of course.
Yeah, we should do maybe a quick question or two because we also have to throw everyone out and have a brief discussion as a committee. I think this one's going to be an easy discussion, but
Anyone,
any questions from the audience?
Zoom? Right.
All right, Veronica, maybe you could make me a host and then we
Okay.
can thank everyone for coming. And I think we'll just be a very, very short. So I'll ping you on Slack when you can hop back on, Veronica.
Cool. Let me make you a host.
And you leave.
Yes.
I'll stop the recording. So you won't hear all the nice things we say about you.
All right. See you shortly.